Hi everyone, today I'm going to be presenting HMMerge, an ensemble method for multiple sequence alignment. We'll be going over the background and motivation for the computational problem we're solving, talk about some related works in the area, and then dive deeper into the key ideas of my method and then the inner workings of it. We'll finish off with evaluation of our method and then the discussion follows. One key thing about multiple sequence alignments is that they are basic inputs for a lot of downstream computational biology analyses. And one of the reasons is that multiple sequence alignments represent homologies, which is in practice alignment of characters in the same column, and it implies that two characters have evolved from the same ancestor. Therefore, getting accurate multiple sequence alignments is of great interest to a lot of downstream analyses tasks such as phylogeny inference and protein structure prediction, and getting accurate alignment then matters in the accuracy of downstream analyses. One problem is that there are a lot of datasets, a lot of biological datasets with sequence length heterogeneity. By that we mean that there are sequences that have long sequence lengths in your dataset, but also short sequence lengths in your datasets. On the left here, I'm showing some sequence length histograms, and you can see that there are two peaks in the top left 16SP all subpanel or bottom right P450 subpanel. Since the x-axes here are the sequence lengths and the y-axis is the count, when you see two peaks, then that means that there's a group of sequences with a certain sequence length or centered around a certain sequence length, and then another group of sequences that is centered around another mean sequence length. And this happens because of evolutionary events such as long insertions and deletions, and also due to modern sequencing technologies that tend to generate many short reads that then have to be aligned to longer sequences. Up and which are both similar methods to HMMerge, and they all three of these methods solve the same problem of aligning fragmentary sequences to full-length sequences. These pipelines all work in the same way, where the input is a set of unaligned sequences and the output is a multiple sequence alignment on all of the input sequences. They work in two stages, where the first stage is the backbone construction stage, where the input sequences are partitioned into full-length and query sequences. An alignment is built only on the full-length sequences, and then an ensemble of HMMs is constructed on the full-length sequences. In the alignment phase, the remaining query sequences that we partitioned out in the first phase will be aligned to the backbone alignment. All three of these methods, up, which, and HMMerge, use the same first stage, but differ in how they align the query sequences to the backbone alignment. In more detail, in the backbone stage, we follow the input sequences being partitioned into full-length and query sequences, and after that, full-length sequences, the backbone alignment is constructed, and we follow a set of decompositions to construct multiple profile HMMs. Now, in the alignment stage, we take all of the profile HMMs and merge them into one giant HMM, to which the query sequences are then aligned. We repeat this procedure for each query sequence and combine them all together at the end to produce one output alignment. Here I am showing some results on simulated datasets where the rate of evolution increases as you go from the left dataset to the right dataset, and the datasets are all arranged on the x-axis. You can see that on the y-axis is alignment error, so lower the error, the better the method is. And if you look at the fastest evolving model conditions, such as these on the right half of the figure, it is easy to tell that up and magus, which are the purple and the pink lines, dominate the alignment error over other methods. So we established that up and magus are the leading methods, at least for these simulated datasets. Now we show the results on up, which, and HMMerge, and we split up the false negative error and the false positive error in the top half of the plot and the bottom half of the plot. As we look closer, we can see that HMMerge, which is the blue line, has lower accuracy or has lower error than which and up, which are its competitors and are also the top methods for these datasets. On the other hand, for the false positive error, we can see that HMMerge achieves a slightly higher alignment error than these two methods. But overall, HMMerge is still able to achieve lower average error than all of the other methods. Now we look at some biological datasets from the CRW website, and we can see that although there are standard methods that perform similarly to our top methods, HMMerge, which, and up, HMMerge is still able to achieve consistently low error compared to other standard methods. And the only other standard methods that come close are the pink bar, which is Magus, and then MAFT oftentimes as well. Future work from my method would be identifying dataset properties where HMMerge is outperforming up. And we also would like to focus on improving the empirical performance of HMMerge, such as runtime memory usage and alignment accuracy, since we have observed that there are certain datasets where HMMerge is not the best method, and HMMerge tends to generate higher false positive error than other methods. We would also like to see the impact of the new alignment method on downstream analyses, such as phylogeny inference. And that concludes my presentation. Thank you.